thanks for the introduction. Thanks for the chance to visit Sydney again. This has already been a wonderful trip. This is joint work with Dai Wenhan, who's a master's student at NUS. He somehow was a PhD. Sorry?
I forgot to get Simon.
Can I keep going though? Or?
Keep going.
Okay. Right, and I think my abstract was possibly a bit scary, so let me just start with some general flavor of how this talk is going to go. So my main theorem will be of the following shape. That some complicated, inexplicit thing, which no one had been able to compute any new cases of for the last 35 years, is isomorphic to some simple explicit thing. Although it's debatable whether these words should be interpreted naively. I'd leave that to you to judge. This side will be in the realm of non-Archimedean geometry, and here I want to wave my hands and just tell a bedtime story, not give precise definitions, just indicate to you the flavor of the shapes and objects that we care about. Here I'll be completely precise, because that won't cost us too much brain power, okay? So, for the rest of this talk, let me fix a prime P. So everything will be in the setting of non-Archimedean geometry. So instead of the reals, somehow we'll be working over this field QP. So this is the p-adic rationals. So this carries a norm, which sort of is measuring how p divisible a given number is. And there's a funny thing you can do with this field, if you have not seen this before. Well, this is far from algebraically closed, so you can pass to its algebraic closure. It turns out this norm naturally extends, and then you can complete this for this norm. And this is notated CP, and you should just think that this is some funny, weird p-adic analog of the complex numbers. It's some kind of metrically complete, algebraically closed field. Okay? And it turns out this is still algebraically closed. This sort of also justifies the notation. Okay, so this is usually sometimes called the field of p-adic complex numbers, which is a truly terrible name, but this notation is not too bad. Okay, let me also fix some n greater than or equal to 2. And now we'll do the following very simple construction. So let me just remind you that if I have a point in projective n-1 space over this field, or really any field, the field here is totally irrelevant. What does this mean? Well, this is the same thing as the datum of some hyperplane, which I'll call hx, in Cp to the n. But again, there's nothing special about Cp. This would work for any field. Okay. Now.
So normally dual, or is that your definition of projective space, or is that?
Yeah, it's hyperplanes in affine space, okay. I guess. But dually, I want to think about it in terms of hyperplanes instead of lines for a reason you'll see in just a second. Okay. So here's an invariant you can attach to a point here. So this will be the dimension as a QP vector space of this hyperplane intersected with QP to the n, okay? So if you think of this as being spanned by n-1 vectors in here, this is measuring the number of QP linear relations between coordinates of those vectors, okay? And so this takes values between 0 if the hyperplane is sort of as irrational as possible, and n-1 if it's spanned by a basis of QP to the n vectors, and all values occur. Okay? So let me state this as a theorem which I'll attribute to Drinfeld, but the history is kind of a little more complicated, so let me not get into that too much. And so this is that there is a natural open subspace, and I'll tell you in what sort of geometric world I'm working in a second. This is traditionally noted omega n-1, and this sits inside projective n-1 space, but now I don't want to just take its points. I have to put a funny symbol here instead, which I'll explain in a second. Okay? Which is characterized by the fact that its points, say CP points, are exactly the x's such that this invariant is minimal. Okay? And what is this decoration? And in what sense is this even a subspace of some other space? Okay, this is the first part where I have to reassure you and just waffle a little bit. Okay, so these are both what people call rigid analytic spaces over CP. What is this? Who cares? It's some non-Archimedean analog of the notion of a complex manifold. Okay, complex manifolds are built locally on rings of convergent power series. You can play the same game over any normed field. Tate figured out how to make this work. People like Berkovich and Huber figured out how to make it work even better. Okay, don't worry about these technicalities. This is some analytic version of projective space over CP, and this is an open subspace in whatever that formalism is. Okay, it's very much not an algebraic variety, as you'll see already in the simplest example. This. So the first interesting case is when n is 2. In that case, this invariant delta is either 0 or 1. And it's 1 exactly when the line, sorry, the hyperplane, which is a line in this case, is a QP line. Okay? And so what are you doing to get this space? You're taking projective line as an analytic space, and you're throwing away its QP points. So you're throwing away a profinite set. Okay? So this probably feels very strange if you're used to algebraic varieties or complex manifolds or whatever. But in this non-Archimedean world, this is an allowable maneuver. Okay? And you should compare. If you did this over the usual fields, something like P1 of C minus P1 of R. Well, this is just C delete R. So up to the fact that you're seeing two components, this is just the usual upper half plane familiar from the theory of uniformization of, say, Riemann surfaces. Okay? And so for some time, people called this Drinfeld upper half space, which is a truly terrible name. There's nothing upper or half about it. Okay? And nowadays, people just typically call this Drinfeld space. Okay? And so this omega n minus 1 has some wonderful properties. So let me try to list a few of them here. So first of all, GLN as an algebraic group acts on projective space. GLN QP therefore acts. And if you stare at how this delta invariant is defined, you realize that it's unchanged if you translate X by an element of GLN QP. Okay? So this subspace certainly isn't stable under the whole algebraic group, but it's stable under the action of the QP points of the group. So GLN QP through its natural action on projective space acts on this subspace. In a certain sense, which I won't make precise, this admits an equivariant retraction onto the building of, let me be a little sloppy, really I should say PGLN, but you can ignore that, of GLN QP. So in some sense, this is locally modeled on the building. This is in fact how Drinfeld built this originally as an analytic space. You kind of glue pieces that are parametrized by the simplices in the building, and the gluing is determined by the combinatorics. This I actually don't know who to truly attribute it to. This seems like folklore, but it can be made precise. This one let me attribute to Mumford and NS2 and Mustafin for general N, is that if I have some gamma in PGLN, which is discrete and co-compact, then it makes sense to form the quotient of this by this. In some sense, it'll act properly discontinuously. And this quotient is a projective variety. Okay, strictly speaking, there's some gaga thing happening here, right? If we did this in the complex setting, we would get a complex Riemann surface in that case. And then we say, okay, this comes from an algebraic curve. The same thing is happening here. Whatever this world of rigid analytic spaces is, can speak about one coming from a variety, and this one has, these quotients all have this property. You should again compare this to the case where n is 2, and we have this analogy, right? If you quotient this by discrete subgroups of PGL2R, you get Riemann surfaces which of course are algebraic curves. Okay?
Not necessarily projective.
Sorry?
Not necessarily projective in that case.
If I said discrete and co-compact, I could keep the word projective. Yeah. There's one more thing I want to put on this list. This is due to Drinfeld. This is that this space, omega n minus 1, and this is in fact how he originally arrived at it. So this is naturally a moduli space of certain p-divisible groups, whatever those are. And if you equip those with certain extra structure, this gives rise to a certain huge tower of spaces over it. So there exists a huge pro et al. Galois cover omega n minus 1 infinity over this n minus 1. And the Galois group here, let me just write a symbol, then I'll say out loud what it is. The Galois group is the unit group of the division algebra over QP of invariant 1 over n. So this is a huge locally profinite group, right? And this is where things really start to seem very different from what happens over the reals, right? The connected components of this are contractible. They don't have interesting covers, right? In this non-Archimedean world, a space that looks like it's defined by analogy with something contractible can still have an incredibly rich theory of coverings and a rich theory of cohomology. And somehow there's much more happening, okay? And this tower is of fundamental importance. So it was conjectured by Drinfeld that its cohomology actually realizes the local Langlands correspondence, and this was proved by Harris and Taylor, okay? And so what I want to talk about is the following much more naive question. So what is the cohomology of just the thing at the base of this space omega n minus 1 itself, okay? And you have to interpret this correctly. So let's look for a moment at the case where n is 2. N is 2, the space is not too bad, right? It's something we understand very well, just some projective line whose cohomology should be really stupid. And then we take away a profinite set, right? This should somehow also have stupid cohomology. And so we can squint and kind of see what the answer should be in this case, okay? And so if you do excision exactly using this definition, you get that the cohomology with compact supports of the thing we care about maps to the cohomology of projective space, excuse me, the projective line, and this maps to the cohomology of this funny profinite set. Okay. Now you know what this should be. This should be just a one-dimensional vector space in degrees 0 and 2, right? And this, okay, I'm being heuristic, but what should this be heuristically? Well, it's just a profinite set, right? Cohomology should just basically be functions on it, or if you define it correctly, maybe locally constant or continuous functions or whatever, blah, 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 right? And so this is only in degrees 0 and 2. It's very silly. This is only in degree 0, and then looking at this triangle tells you what this should be. And Drinfeld did this calculation, I think, in 1981 or something like this. And so what you get here is in degree 1, you get this in degree 0 mod this in degree 0. So you get functions on P1 QP modulo constants, but shifted, so in degree minus 1. Sorry, in cohomological degree 1. And then in degree 2, you just get this. So let me write this like this. Okay, and the notation here, why am I writing this and not QP or QL or whatever my coefficients are? I want to emphasize that we still have this group action everywhere. And when I say we want to compute the cohomology, we really want to compute it as a representation. Otherwise, the answer is silly. The answer is just going to be it's some huge infinite dimensional vector space, okay, with no structure. Oh, sorry, minus 2. So this was already done by Drinfeld a long time ago. And if you haven't seen this before, let me point out that this as a representation is actually quite beautiful. So this thing, without the shift rather. So this is irreducible, it turns out. And this is usually called the Steinberg representation. Okay. So continuous functions on P1 QP has length 2, you kill the constants, and then that turns out to be a simple representation, okay? So without the action, the cohomology would just be some huge structureless vector space, but with the action, it's just in 2 degrees, and in each of those 2 degrees, it's irreducible. So the answer is actually quite lovely. Yes? Please ask questions, by the way.
So, the representation of what?
Ah, yeah, sorry. In this case, I want GL2 to act. Of course, you could pass to PGL2, but somehow I want to keep the whole GL2 available. Yeah, it's coming from this action, right? Whenever you have a space with a group action, the cohomology will be a representation, right? This is how we make interesting representations appear in the world. Other questions?
So 2 comments and 1 question.
Please.
So first comment is that so at the time that Drinfeld did this, people were aware of the fact that SL2R has a whole bunch of boring representations and then some interesting representations that show up in functions on the upper half plane. And so, if you're motivated by SL2R, this is very natural. And then, of course, so last semester, 2 semesters ago, there was the linguistic seminar. And, of course, everyone learning the linguistic seminar sees the analogy with that construction. But it's kind of crazy because my understanding is Drinfeld did this and then he worked out the case of the Drinfeld curve as a kind of...
Yeah, I believe that's correct. Yeah.
Which is nuts. This is like way more complicated than the linguistic story. And so that division algebra, is that the kind of most complicated division algebra of dimension n?
Yeah, it's the one of Hasse invariant 1 over n. So.
Yeah, I can't remember what the Hasse invariant is, but I'm happy to think it's the most complicated one.
So if you take the unramified extension of QP of degree n, it's generated freely as a vector space by that together with a symbol like capital pi or whatever.
Yes.
And the relation that you impose is that A times capital pi is capital pi times the Galois generator acting on A. So you can also embed it into matrices in some way. But yeah, in some sense, it's the simplest division algebra, not the most complicated one, I would say.
So the simplest of that dimension.
Or most irreducible or something. Yeah, exactly. Yeah. But I didn't notate all that on the board because this was just meant to be some background culture thing. This won't appear in the rest of the talk. I just want to look at these guys. Did you have a question also, you said?
That was the question.
Oh, okay, great. Okay, anything else? Okay. Oh. Let's see how hard I can break these by the end. All right, so that's the case n equals 2. Of course, we're mathematicians, we're ambitious. We can ask what happens for general n. By the way, as a motivating comment, let me point out, why would you care about the cohomology of this omega n minus 1? Well, if you care about algebraic varieties, and you want to compute the cohomology of one of these things, by some descent, this will tell you you have to understand the cohomology of the thing upstairs, which in the real numbers world would be really silly, together with how this group acts on it, or more precisely, what the homology of this group acting on the cohomology of this would be, okay? So in the real numbers world, this part of the story is very silly, and we just say, oh, it would be a k pi, it would be a k gamma 1 space or whatever, right? But here you really have to figure out what this is contributing, and then incorporate this, okay? And so this part of the story was actually important in Harrison Taylor's work, so.
But philosophically, we should think that this tower kind of becomes simply connected to one another.
Yeah, that's right, in some sense, yeah. Yeah.
You're talking about cohomology, you didn't say any word about what?
I don't want to. It's L-adic cohomology. You can make that work, but let's just be heuristic. Yeah. It's actually quite subtle to get it working right in this formalism, but that's known now how to do that. Okay. So what will these look like for n bigger than 2? So to answer this, I have to write down some family of representations, which will turn out to be the relevant ones to describe this. So this construction is rather concrete, and I find it very pleasant. So for any I, which will be just a list of integers I1 less than I2, less than IK, with the condition that they're all between 1 and n minus 1. Okay, so there's 2 to the n minus 1 options for capital I. It could be empty, it could be the full thing, it could be anything in between. I'm going to let pi in GLN be the lower triangular parabolic, whose levy is just the diagonal product of the following groups. So I want it to be GL I1 times GL I2 minus I1, blah, 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 all the way up to GL IK minus IK minus 1 is GL n minus I Okay, so if you don't like words like parabolic and levy, just picture the obvious sort of block lower triangular subgroup, which looks like this on the diagonal, okay? So now let me be a tiny bit more precise about my coefficients and my exact functions. So here LC means locally constant, and I will take pi of QP now, acting on the left on GLN of QP, and then take the quotient. Okay, so this is a profinite set. This is just the QP points of a partial flag variety for GLN. And I want to consider locally constant functions into QL for some auxiliary L that I won't even write on the board, okay? So this L is the same L as in my cohomology, right? But just pretend it's not really important. So this, just by translation on the right, this has an action of GLN QP, okay? This is obviously a huge vector space, but as a representation, it turns out to be very nice. So this is a smooth, I'll remind you what these words mean out loud, an admissible GLN-QP representation. So smooth, these are both finiteness conditions, if you like. Smooth means that every vector in here is stabilized by an open subgroup of this topological group. So this is already a kind of a continuity condition, if you like, for the natural topology here and the discrete topology here. And admissible is sort of a condition that pushes in the other direction. This says that if I pick, conversely, some open subgroup here, and I look at its fixed subspace, it'll have finite dimension. So if you pass to fixed vectors for any open subgroup, you get a finite dimensional thing, and then somehow, because it's smooth, it'll be a co-limit of the fixed spaces for open subgroups. And so together, these tell you that this is in some sense a small thing, and not in fact a huge thing. It's kind of a very natural co-limit of finite dimensional things, okay? And in fact, it's even more finite than that. It turns out to be of finite length. I can even tell you what its length is. It's 2 to the size of I. And even better, it has a unique irreducible quotient. So it's very far from semi-simple. It's complicated in terms of how it's built up from its Jordan-Holder constituents. And in fact, it's complicated enough that there's a unique irreducible quotient. So with a unique irreducible quotient, which I'll denote pi I. And so these are the building blocks for the answer to this motivating question now at the top of the board. And so you should imagine here that there's two extreme cases. So if I is empty, pi I is the trivial representation. In this case, this whole setting is degenerate. The parabolic itself is GLN. So this is GLN mod GLN. So this is a point, and so nothing's happening, okay? And at the other extreme, if I is as big as possible, so it's really everything, then pi I is this Steinberg representation again. So this is some distinguished representation that exists for every group, okay? But in general, you have a bunch of stuff in between. You should imagine that as I gets bigger, pi I also gets bigger in some sense, even though as a vector space, it's just infinite dimensional, okay? And these are the building blocks for the answer. Any questions about this definition before I proceed? These have analogs over finite fields also, which maybe are familiar to many of you or some of you. Okay, so here's a theorem. This is due to Schneider and Stuhler. This is from 1991. And so they proved the cohomology of this Drinfeld space. And let me now be a tiny bit more explicit by putting a QL here. So this is some kind of p-adic et al. Cohomology. And then I'm going to normalize things by shifting by the dimension. So if we were in the world of projective varieties, now the cohomology would be sort of centered in degree 0. You would expect stuff in negative and positive degrees, kind of a symmetric interval. It turns out this is very asymmetric. So it always starts with the same thing that it started with in case n equals 2. And now because of this shift, there's not a shift there. So you get Steinberg, which remember is pi subscript 1, 2, 3, 4, 5 up through n minus 1. It turns out the next thing you get is pi subscript 2, 3 of 3n minus 1 shifted by minus 1. And then you continue like this. You delete more and more numbers at the beginning string, and you shift upwards by 1 more degree every time. And so then it terminates like this. Lastly, you have pi n minus 1 shifted by 2 minus n. And then finally, this is the empty set. Pi I is trivial, so trivial representation shifted by 1 minus n. Okay? This is a pretty weird looking expression, right? Again, it's very asymmetric. It's not centered in degree 0. It's all in non-negative degrees. But there are some patterns you can already see. In some sense, they're getting simpler as you go up. If you believe my heuristic that these are smaller in some sense when I is smaller, until you get to the very top, you have the trivial representation. And also the total length is n minus 1, which agrees with the total length of the cohomology of full projective space. Somehow if I just put p n minus 1 here. Okay. Sorry, total length is n, excuse me. And this is a hard theorem. I should say already in this case, you have to be very, very ingenious to prove this. And their strategy is to stratify projective space by this delta invariant. It turns out the stratum where delta equals a fixed positive number is related to omega superscript n minus 1 minus I. And so this opens the possibility of proving this by induction on n, which is what they do. Okay? They also use other facts that I mentioned, this retraction onto the building and blah, blah, blah. And to give you some idea of, well, how hard this is, somehow, I don't think there's been a second proof of this in the last 35 years since they first proved this. Okay? Does this statement make sense? Okay. Now, it turns out this is the tip of a very large iceberg, and this is what I want to kind of approach in the main theorem. So more generally, so recalling that projective space is really just a Grassmannian of, okay, now I'm going to switch to lines rather than hyperplanes. It turns out that for any Grassmannian, say dn, so this is the Grassmannian of d planes in n space, there is a natural GLN QP invariant open subspace, excuse me, which I will write dm, ADM. This stands for admissible, and this will sit inside the whole thing. And I'm secretly always working in this analytic world. These things don't make sense otherwise, okay? So if D is 1, you get exactly this Drinfeld space. This is just projective n minus 1 space. In general, let me just say one word about where this is coming from. Dn. This is the image of a p-adic period map. From a moduli space of p-divisible groups. Now, what do these words mean exactly? Don't worry too much about it, okay? These are something like a p-adic version of a Hodge structure. Variations of Hodge structure naturally have these period domains associated with them. The simplest example is this, which is still on the board, okay? And it turns out you can play this game not just for projective space in this non-Archimedean world, but really for any Grassmannian, okay? And for whatever reason, people in the field call this the admissible locus. I don't want to explain why that word is used. But it's there. It was defined in this generality in 1996 by Rappaport and Zink. And again now, I keep moving the boards the wrong way. Now the same question makes sense. Can you compute the cohomology of this thing, right? And for some normalization reason, I always want to shift things by the dimension, which is d times n minus d. This makes life nicer. It's consistent with the shift that I put here. Okay, so when D is 1, this theorem answers the question. Okay. When D is bigger than 1, there's only one example I know of, and it's not even in the literature. It's just in the literature in principle. Okay, so if n is 4 and D is 2, and there's a paper of Orlik from 2005. He gives a simpler example, and I convinced myself his methods would also work to prove the following. So let me just say in principle, which I don't think is too unfair. And so in this case, the answer turns out to be the following, which is, as you'll see, somewhat unguessable. So there's now a positive shift here. Remember, n is 4, so my I is supposed to be integers between 1 and 3, right? And it turns out next you see I sub 1 comma 3 and pi 1 minus 1, 3 minus 1. And then the trivial representation in degrees 2 and 4. And that's the answer. Okay. And the reason that this case is doable is that, again, the boundary, the complement of this space in the ambient Grassmannian is somehow explicit. In this case, it turns out to be describable in terms of omega 1 in some funny way. Okay? In the lingo of the field, what he's really proving is something about the cohomology of the weakly admissible locus, which is a human proxy for this inhuman thing. Okay? And there's a finite set of cases where they coincide. Okay? And it's so hard to compute anything in this field that even though all he computed was the cohomology of some proxy, this was also published in Invenciones. This paper was published in Invenciones too. Okay, so anytime you can compute anything in this field, it seems, it's kind of a decent theorem. Okay, and then people were stuck, I would say, since then. So no new examples since then. So maybe the first interesting example beyond here is when n is 5 and d is 2. And so here the boundary is a total mess in a technical sense. Okay, it's not built from things you understand. It's built from things that are even worse somehow than the ambient space, so there's no room to do an induction. Okay? Now, nevertheless, I can tell you what the answer is in this case. As you'll see in a minute, I have some machinery that tells one how to do this, and there's a certain delight in actually working out these examples, at least for me. So remember, n is 5, so my boxes of integers have to be all between 1 and 4. 1, 2, 4. Yeah, yes, that's right. That's the answer in this case. So it has length 10. This funny Steinberg thing occurs twice, and then again you see similar patterns to what we saw in other cases, but now it's kind of less clear what is actually happening quantitatively, right? The numbers are getting smaller as we go up in degrees. You still see the trivial representation at the top. In fact, there's sort of a tail that has length bigger than 1 where you see the trivial representation. But the boxes that you get are kind of random looking, right? Why does 1, 2, 4 and 2, 3, 4 appear, but not, 1, 3, 4? Not sure. Okay, does this example make sense? At least the formulation.
It's that when we were discussing, but like
Yeah.
a very basic, remarkable thing is that it's a semi-simple.
Yes, yeah, this is not even obvious. So in general, there's a very complicated non-vanishing set of x groups between any one of these pairs of pi i's. Like x pi I comma pi j will always be non-zero in some positive degree. So there's a priori no reason at all that this should be split as a direct sum of semi-simple things up to shift, right? A priori, it could be very, very non-split. And there's no soft structural reason that I can see why this is true. It just is a consequence of the main theorem. Okay.
So in some sense, when you construct these things, you demonstrate there's a whole lot of that.
Yeah, exactly. Yeah, so these vividly show that these do have non-trivial x. And in fact, you can inductively compute the x somehow from knowing what the Jordan-Holder series of these are. By somehow, let me not get into that. But yeah, these pi-i's have a very rich internal theory. And then somehow, the fact that they show up here in nature. But in this completely semi-simple way, I find odd. Okay? I'll make some more comments on the structure of this later after I tell you a general result. Okay. All right, so as you may have guessed, this is not somehow the only case where I can tell you the answer. It turns out there's a completely general thing one can now do. Oh, and before I forget, if you want to see a bunch more examples that would take way too long to write on a chalkboard, you can go to whatever my website is, which is something.net. You can figure it out using Google, and then /Sydney.pdf. Okay, there's a ton more examples there, which you can also choose not to look at if this seems disgusting, but I find this very fun that you can actually enumerate these things. And where is this crazy answer coming from? So this is now what I want to tell you. So this will be the main theorem. And in case you haven't guessed, the template that I alluded to earlier, the something complicated will be an even more general version of this, cohomology of some crazy space. The something simple will be a kind of direct sum of certain pi-i's with certain shifts. And I'll tell you exactly what the formula is. Okay?
I went to your website and said your connection is not private.
I don't know what to do about that. It's the main result. Okay, so to formulate things in their natural generality, let me introduce a tiny bit more notation. So let me set g hat to be gln, but now I'm thinking of this as an algebraic group sort of on the other side of some Langlands duality. So this is over QL, and this contains the usual Borel and the usual torus. So this is just upper triangular stuff. This is diagonal stuff. I want to identify characters of this diagonal thing with z to the n in the usual way. Just read off the exponents. And here, there's an obvious map, which is just sum the exponents. So this, I call this degree. This just records what the character does on the center, right, which is gm. Now here is the true generality in which this story can be studied. So for any dominant weight for this dual group, here plus indicates dominant, there exists a pair x mu admissible inside x mu. What is the nature of these spaces? This is some kind of Schubert cell. In let me use the word funny, in a funny affine Grassmannian. Okay, the technical meaning of the word funny here is that it's the B de Rham affine Grassmannian, but don't worry about what this means, okay? It's just some kind of affine Grassmannian. This thing itself is very simple. This has simple cohomology. This, as the notation suggests, is some more general version of these strange open subspaces that we're trying to get our hands on. Okay, so this is some GLNQP invariant open subspace. Okay? And so the most general version of the problem is to compute the cohomology, which again, I'm being a little sloppy about whatever the definition is here, of this thing. And in general, if mu is not minuscule, these have singularities, and so you know you should really put the IC sheaf here, okay? And let me connect this back to the numerology over here. So if mu is a bunch of ones followed by a bunch of zeros, and I put d ones here and n minus d zeros, then you get exactly this Grassmannian setting. Okay? So these mu's really parameterize the examples on that board, but you can do any mu, or at least ask the question for any mu, okay? Does this setup make sense, modulo the fact that I'm not defining these things?
Maybe if people want a story, normal delinguistic varieties are some open subset inside a Schubert variety.
Right.
It's kind of that fun version of that.
Yeah, that's a good heuristic. You can also think that this is telling you how to modify some vector bundle in a funny way on some funny Farg-Fontaine curve. And this is the locus where the modification is semi-stable. So it also has connections with GIT notions like semi-stability. Okay, so our main theorem will completely compute this cohomology. And to explain the answer, I need a tiny bit more notation, but this is all on the g-hat side, and it's all very sort of down-to-earth combinatorial simple notation. So please bear with me for a tiny moment. Okay. So first, inside this space of weights, there's a subspace of stuff of degree 0. So this is the stuff in the kernel of this map. And so this is the span of the usual simple roots. So anything here written as mi alpha I, 1 less than or equal to I less than or equal to n minus 1. Sorry, the alphas are what you think they are. Alpha I on something in this torus is just ti plus 1 inverse. So inside the whole weight lattice, we have this subspace, things that can be written like this. So I want to attach to such a thing two integers. So this will be the sum over I such that mi is strictly positive of 1 minus 2 mi. So this is a non-positive integer. I'll also attach to it one of these i's on some box of integers. This is also going to be of very simple nature. It'll be the i's such that the opposite holds, such that mi is not strictly positive. Okay, so nothing funny happening here. But now something funny will happen. And this will look weird enough that I will give several examples of it. So for any d and z, I'm going to define an element of this weight lattice by a very odd-looking formula, which will have two parts. And so here I'm just using this identification, but then I will somehow also mix it with this definition. Please ask me if this is unclear. So this is the ceiling function, which I can never write nicely. Through d minus ceiling. Okay, so that's already some funny thing, but this is a well-defined element in this weight lattice. And then I have to add to it the following also funny thing, sum over j strictly between 0 and the GCD of d and n of alpha subscript j times n with this GCD depleted from it. Okay, so this looks completely weird and insane. So let me give you a few examples of what this tau d looks like for orientation. So, for example, for any n greater than or equal to 2, tau 0 is just the 0 element in the weight lattice. And tau 1 is just 1, and then n minus 1 zeros. Okay? Let me just give two or three more examples at random. If n is 5, tau 2 is 1, 0, 1, 0, 0. And tau 3 is 1, 1, 0, 1, 0. Okay? So it's very easy to see what this is in any given case. The formula just is what it is, okay? Okay, with this prep, I can state the main result. So theorem. Yeah.
So I feel like this formula compiled last time around and compiled formula.
Yeah, please.
Alpha J. So can you just explain the subscript on alpha J? Alpha subscript what?
Sure, these are the alphas, right? If j is in here, right, but then I multiply, so this is an integer, right? This thing. And then j times that integer is still between 0 and n
Okay, yeah, okay.
because of the nature of j. So this is a sum over kind of an arithmetic progression of certain alpha i's, but only the ones where the subscript is divisible by this.
Yeah.
And so in the case where the GCD is 1, this sum is void. That's why tau 1 is so silly. So if d and n are co-prime, this does nothing at all. This is totally empty. But if d and n have a sort of large common divisor, then there will be many things here. Okay, so here's the formula. So let me fix any n and any mu. And let me abbreviate d as the degree of mu, okay? So in the projective space case, the degree of mu would be d, which is consistent with my notation, okay? Sorry, in the Grassmannian case. D equals d in that case. So then there's an isomorphism of the cohomology of this admissible locus in x mu. Sorry?
What was your comment about d in the dimension and consistency?
Oh, here I'm defining d to be just shorthand for this, but in the Grassmannian case, d was something else.
Yes.
But a posteriori, those are the same d. The degree of a mu of this shape is the number of ones.
Okay. Yeah. But
So.
you're not claiming anything about dimension.
No. This mu is not minuscule, completely random. Any mu you want, up to being dominant. Okay? So then here's the formula. Direct sum over nu. I'll make some comments on this formula after I write it. Of degree d. Pi subscript the box of integers attached to tau d minus nu, shifted by the shift s evaluated on tau d minus nu, plus GCD of d and n minus 1. And how many times do you count this for a given nu? You count it dimension of the new weight space of v mu, number of times. Okay, so I find this formula completely weird, but it is true. And you can check, if you really want, that when n is 2 and d is 1, this does recover Drinfeld's calculation. Or more generally, when d is 1, this recovers the Schneider-Stuhler theorem. Okay? So, any questions just about this statement, about this equation, before I make some comments on what this may or may not suggest? Okay, as a corollary, let me point out, so in particular, this comes back to Jordy's comment earlier. The cohomology is totally split in the sense that it's a direct sum of shifted irreducible representations. There's no funny exts or non-formality happening there. And its total length, well, what is its total length? Each of these is a shifted irrep, and then you count it this many times, and I'm summing over nus. And so if you add this up over all nus, you just get the dimension of v mu, which you can check is also consistent with the examples I gave. Okay? As far as I can tell, there's still no soft reason why this should be true. It only follows a posteriori from this weird formula. That's something I wish I understood better. Maybe I leave this here and you can contrast it with this example if you like. Okay. And of course, whatever examples are in this file, I did it using this and variants of this. So we had a long discussion at Tuesday lunch about how to give a good talk. After that discussion, I've decided that I will say basically nothing about the proof. I can come back to that in the questions at the end if people are curious. For now, let me just make some more down-to-earth comments and point out some things I don't understand about this formula. Okay, so some first observations. Questions? And again, if you want to see sort of why these are reasonable, I encourage you to look at these examples and compute your own. If you're a programmer, I can't program, so I did all the examples by hand. So first of all, we have this observation that I already wrote, that it's split of this given length. Next is very asymmetric. Unlike the cohomology of, say, a projective variety or whatever, where once you normalize it in the way I did, it would be centered around degree 0. So here you can see that it sits in what interval? Well, what's the smallest that this can be? Remember, this is always non-positive. So the case where this S thing is 0 is sort of the furthest to the left you can be. And there you'll just have this. So it sits in degrees 1 minus this GCD, right? Which is non-positive, but for n in fixed, right, this is some bounded quantity, right? Even if mu is ridiculously huge, this only depends on d, the degree, and n, right? And it divides n. So this is really between 0 and minus n, if you like. And then the upper bound, which you can prove that this is the maximum shift occurring here, is the usual pairing of 2 rho with mu. Okay. This, by the way, is the dimension of this x mu in whatever sense. Okay, so you expect the cohomology naively to be sort of in degrees minus this up to this, but it's not that. Sort of on the right it is this, but on the left it starts much, much closer to the center. Okay? And in some cases it starts at the center. Right? So when the GCD is 1, which is what was happening here, you really start in degree 0. Okay, what does the lowest degree part look like? Well, this shift thing is 0 if and only if, oh, did I erase it? I hope not. This shift thing is 0 if and only if this never happens, right? All the mi's are non-positive. And that happens if and only if I is as big as possible, right? So I is every possible number, which is to say pi I is Steinberg, if and only if this S is 0, right? And so this already tells you what the lowest degree part will look like. So Steinberg fills out the part in degree exactly the lower bound 1 minus this GCD. And what is the multiplicity with which it occurs? Well, kind of staring tautologically at this formula, you want to add up this over all nu such that I is everything. And when you stare at the definitions, you realize that this boils down to the following thing. So this is with multiplicity. Sum over nu with the property that tau of d is less than or equal to nu in the usual dominance ordering of dim mu lambda. So first thing I don't understand, what is this weird sum? And you can interpret this question however you want. Is there a formula? Is there an asymptotic? Is there some special pattern when mu is minuscule? I asked ChatGPT and it told me a bunch of nonsense. So you could probably do better.
And tau d is nothing like an extremal weight or something like that.
Sorry?
Tau d is nothing like an extremal weight of the module.
Right. No, I mean, tau d is very small, right? You should think that, like, are the examples still here? Right, tau, if d is like 2 or 3, whatever, tau d is this shape, right? Whereas mu could be a very, very far out in the alcove dominant weight or whatever. You should really think that this, I mean, a toy case array would just take this to be 0, right? Then you're just summing over the obtuse cone the dimensions of the weight spaces. It's a very weird formula, but nature is handing it to us somehow. Okay. At the other end, you can already see in this example, when you get really close to the top, so this number 6 is, in this case, is this 2 row paired with mu, right? When you get really close to the top, you just see the trivial representation with some shifts. And this seems to be a general phenomenon. So in degrees near the top degree, 2 row mu, the cohomology has trivial GL and QP action. And agrees with the tail in whatever sense, or the truncation, let's say, above some degree that I don't really know, of the cohomology of the full thing. So note I did not write the word admissible here. This is the whole Schubert cell, right? And this is extremely concrete. So this is just V mu, but graded by 2 row, if you like. Say by GM acting through. G hat, right? So this is part of the basic formalism of the geometric Satake equivalence, right? This will be V mu, but then the pieces in different degrees will exactly correspond to the grading of this V mu by the restriction of this action, okay? And the reason I put a question mark is that I don't know what this question mark number should be, okay? Where does this tail of trivial representations at the top start, okay? So what is the optimal point at which you can start this tail? And don't be too optimistic. If you look at some of the examples in this file, you'll see that when you allow bigger numbers, there will be situations where this sort of monotone drop in complexity as you go up in degree disappears. You'll have situations where like trivial, this will occur in some degree, and then this will occur in the degree above it, and then this will occur in the degree above that, okay? So they start to become interleaved in funny ways if you do more examples. So that's why partly why I don't have a good guess here. And let me end with one last question. And this is what I maybe would really like to understand, because this is supposed to be a test case for a much more general family of computations like this. And in that more general setting, this question I would say is of basic importance. So what is the largest degree in which pi I occurs? Say for fixed I. And varying mu. Okay? And again, I leave this as a slightly flexible question, how exactly you want to interpret this. There's 2 cases where you can already see something though, right? For Steinberg, if you want an answer that really doesn't depend on much, the answer is 0, right? It always sits in this very explicit degree, which is between 0 and some negative number. Okay?
So you said it fills out that part, but
Yeah.
is the other statement that there's nothing in any other degrees?
No Steinbergs in any other degrees. Yes, that part is all Steinbergs, and that's the only place Steinberg can happen. That's right. Right, so Steinberg, the answer is 0, and the trivial representation, the answer is 2 row paired with mu. But the intermediate cases I don't understand. There's a conjecture of Koshikawa and Shin for an upper bound, which seems true in all examples, but it also seems far from sharp in all examples. So maybe I write this conjecture and then I stop. So conjecture, this is a specialization of a more general conjecture of Koshikawa and Shin. And again, this seems not sharp in general, so I would like to find a sharp conjecture here so that I can go back to their more general setting and figure out what the right true sharp conjecture there is, so that this degree is less than or equal to the maximal weight of GM me formulate it in a hopefully down-to-earth way, acting on V mu through the following sequence of group homomorphisms. So here I have 2 rho, but rho is for the Levy subgroup in in G hat of the same shape as as the Levy of pi. So this goes to mi hat, and then this sits inside G hat. Okay. So if I is as big as possible, this is a torus, and it has no co-roots internal to itself. So this is the 0 homomorphism, so you get 0, which is what the answer was supposed to be for Steinberg. And conversely, in the trivial case, this matches also. Okay, but I think one can do better, and I don't understand what the right statement should be. So there's a lot I don't understand here, and I'm hoping some other representation theorists will look at this formula and say, oh, this reminds me of XYZ thing from this paper that people have forgotten about. But let me stop here. Thank you very much.